Welcome everybody to our webinar on modeling heat transfer in fluids with COMSOL Multiphysics. My name is Ksenia Semina. I'm a marketing executive at COMSOL UK. In this webinar, you will learn about the different methods for modeling heat transfer in fluids, from simplified approximations to high-fidelity non-isothermal flow coupling. Our speaker today is Andrew Young, who is a technical manager at COMSOL UK. Andrew is specializing in heat transfer and fluid flow. He studied mathematics at the University of Strathclyde, where he also earned his engineering degree in medical devices. His research involved the CFD analysis of patient-specific cardiovascular modeling. Before we start, I'm going to briefly run us through some introduction to the GoToWebinar software in case you haven't used it before. You can see control panel on the right-hand side of your screen. Please use questions pane to submit any questions as they arise during the webinar by just typing them in a box. Answers won't be displayed. Instead, towards the end of the webinar, about 30-35 minutes in, Andrew will answer the questions that come in. Please don't miss out on this opportunity and submit your questions early. We will try to answer all your questions, but any we don't get to will be followed up afterwards. Also, everyone will receive an email within 24 hours with a link to the recorded event, so you and your colleagues can watch the webinar on demand. Okay, enough intro information. I'm going to hand over to Andrew.
Thank you, Ksenia, and welcome everyone to today's webinar. Thank you for tuning in. So we'll start with a very brief introduction to COMSOL Multiphysics. I hope you all know what the software product is, but we'll give you a high-level overview, and then we'll jump straight into looking at heat transfer in fluids and the different features that exist. We'll run through the low cost and high cost as a summary, and then we'll delve a bit deeper into each. For each application, each approach, we'll be doing a live demonstration. One, we'll be looking at coffee cooling using a low cost approach. Then we'll be looking at a high fidelity modeling where we do fully resolved simulations. As Ksenia said, we have a question and answer session, so please do ask your questions as we go, and we'll do our best to answer them live. If we don't get around to that, we will follow that up in technical support. Then I'll hand back to Ksenia, who will close the webinar and discuss the next steps and other further resources and things to be aware of that COMSOL is actively, the events that COMSOL has active. Okay, so COMSOL Multiphysics is predominantly finite element-based software simulation package that uses partial differential equations to solve a wide range of classical different physical phenomenon. One of the key strengths of COMSOL Multiphysics is in the name. It's the ability to couple those different classical interfaces or physics disciplines into one integrated model. Here we see on the slide a wide range of these groups. And today we'll be focusing on fluid and heat. That can very easily be coupled with other physical phenomena such as structural mechanics, looking at thermal expansion, or we can have a look at optimization and some of the other extended capabilities. COMSOL is always flexible enough to define your own equations, whether that's your own governing equations or you want to load in your own experimental data. We also have an application builder that allows you to take your fully built COMSOL model and design your own user interface for it. This will still run the full simulation model, but you get to control the inputs and the outputs so that anyone can use simulation and the burden no longer rests on you, the simulation expert. Here we see the COMSOL product suite, and it's a modular software package. So to be able to cover those wide range of physics disciplines, we have dedicated add-on modules to our core product that give you predefined specialized couplings for how to solve the equations of interest. What I'd like to highlight from this slide is we have this great new product called the COMSOL Compiler. I encourage you to look at some of our webinars that discuss how you can distribute your apps worldwide using this functionality. And we also have the composite materials module that's new for 5.4, and again we have many webinars covering what the functionality there is. Today the functionality is all found in the heat transfer module, but there's also an overlap. So these add-on modules contain extra functionality or overlapping functionality. So it's best to get in touch with your COMSOL representative so that we can give you the package that is most cost effective for your simulation requirements. Okay, so heat transfer in fluids. We're going to split these into low-cost models and high-fidelity models. So first step is we don't even have to simulate fluids to be able to account for heat loss due to fluids. This is called boundary convection, and we can use either a fixed heat transfer coefficient or library of empirical values. So even within that simplification, there is a grade of complexity. Then we have domain level approximations, where again, we're not solving for fluid flow. We can look at enhancing the conductivity of a fluid. We can treat a domain as uniform temperature, and that's one that we'll be using in our live demonstration. Or you can even impose the velocity. If you know an analytical solution, or you have some data that's already computed elsewhere, you can impose this within a model. You don't need to solve for it. But with COMSOL multiphysics, you still can solve the full computational fluid dynamics model. For that, we have a conjugate heat transfer to couple a uniform temperature field for both the solid and the fluid phase. What drives that convection? Well, we'll discuss these in greater detail in the second set of slides, but we have both natural and forced convection, which is available in both laminar and turbulent regimes. If you don't know what that refers to, we'll unpack that a little later on. Also, you can enhance your flow models with dedicated boundary conditions, such as inflows and outflows, open boundary conditions, and even lumped quantities like screens and fans. So all that complexity is available as you enhance your model step by step. So, as I said before, what's the benefit of the heat transfer coefficient? Well, it means that you don't have to solve for the fluid domain. What we have instead is a boundary flux with an equation where we specify some ambient external temperature, and we use the computed temperature of the solid domain to define the heat flux. This value h, to simplify, could be set up with a fixed value, but it is something that's known with high accuracy in a number of predefined cases, whether that's taken empirically or from analytical solutions. And COMSOL has many of these built in. So we have a library of these coefficients for internal or external flow, and we can see the diagram on the right-hand side indicating the difference, for natural or forced convection. So all permutations of internal, external, and natural and forced convection regimes. It's also available for a range of geometries, including walls, plates, cylinders and spheres, and narrow chimneys. Again, we have an indication on the right-hand side of the slide here, where each value of h will depend upon different input parameters, and we can see one of these analytical expressions on the right-hand side. But if you'd like to learn more, we do document every single equation with the sources and the references where that's come from. So I'd like to point you to page 270 of the Heat Transfer Module User's Guide if you have any further interest in using these or finding out more about them. If you want to see how you use them, this is a great tutorial taken from our application libraries. It's looking at thermal stress in a turbine stator blade. What's really interesting here is that within the same model, you can use different types of this heat transfer coefficient. So in the screenshots, I hope you can see that one is using the simplest case that we spoke about, where we have a heat transfer coefficient that's a fixed numerical value. And secondly, we have a more complex analytical expression that actually incorporates local data, so x being our local x coordinate. And even still, we have different reference temperatures, one for inside the fluid domain that has forced convection, and one for the external where we have the temperature of the gas. So this is a great tutorial, and you can find it in the application libraries under the heat transfer module, thermal stress, and turbine stator. It's also available on our website. Okay, so that's the boundary convections. What about the domain level? Well, the first simplification, and we're going to use this in today's example, is an isothermal domain. If we're interested in, say, a cup of tea or a mug of coffee, or in this case, a flask of coffee cooling down, we're not really interested in the fine resolution of the temperature gradients and the convection currents within the fluid that may be occurring. So what we can do is negate all that spatial resolution and solve for one lumped temperature value, so a uniform temperature value. But what it retains is that energy balance, and you can interact with different boundaries and features in a wide different, whether you're specifying continuity of temperature, continuity of mass, or specifying some kind of conductive or convective heat flux around its surroundings. But this is great because we're solving for 1 degree of freedom and we don't need to resolve the thing in full. Then we come to heat transfer in fluids, and we don't yet need to compute the velocity field. So the first option, we see it on the right-hand side, is we can actually specify an analytical velocity profile without solving for fluid flow. And this has been taken from one of our tutorials in the applications library, the isothermal unit cell mixer. So again, have a look on the website for these tutorials. You can also not solve for the fluid, but you can still include the effect of natural convection by enhancing the conductivity of that fluid domain. So this is a sub-feature that previously was found as an advanced option in 5.3a. In 5.4, it's now its own feature where you can use the ratio between convective and conductive heat flux, i.e. the Nusselt number, to scale that thermal conductivity of the fluid. We have a predefined library of equivalent conductivities, as we see on the right-hand side, but you can also specify the Nusselt number yourself. Okay, so we're going to use some of these simplifications, these lumped models, to look at a live demonstration of coffee cooling. So we have coffee cooling in a thermos flask, and we're going to use the isothermal domain for the coffee and heat transfer coefficient for the outside. So let me switch to a model that we already have partially set up. Let's have a look. We're in the COMSOL GUI now. We see we've got some geometric parameters set up and we have some physical parameters set up. So in COMSOL, you can now group your parameters based on what they're being used for. Then in this model, I've already got the geometry as well as some very useful selections. So I don't need to continually select this group. I can access it via a selection. We also have ambient thermal properties here, so this is something that can be used by the heat transfer interface itself, and all my materials are already set up. We have this single layer material, which is where we specify the thickness. This ties into the composite materials module, which is a new product, but that functionality is available throughout the entire software suite. So we can actually say that selection that I referred to, the shell, we're actually able to specify what the thickness is by referring to our parameter dshell. Like so. There we go, that's our parameter. And the material properties that are used are taken from steel. Okay, so first things first, we want to add in our initial values for the coffee. At the moment, everything is at the ambient temperature as specified by this drop-down menu. I can right-click to add in different domain and boundary conditions. So in this case, I'm looking to add in initial values, and I can click the coffee domain there and use my parameter. So let me just type that in, T coffee. But you may have noticed that there was no isothermal domain when I clicked there. This is an extra feature that's not active by default. So we go into the heat transfer and solids interface to enable this functionality. With the checkbox isothermal domain, we have a new feature, default feature already active. And when I right-click, we now have this new domain condition for the isothermal domain. So I add that and make it the same selection, just one click, so that's quite straightforward to do. And then I need to look at the isothermal domain interface. Notice that COMSOL has automatically selected what boundaries these are, and I need to specify the interface type. So for this, I'm going to use a convective heat flux and just specify quite a large value, so there's not much thermal resistance between the two domains. Next, I want to add in my heat flux conditions. So again, I can right-click and select the heat flux option. Where am I solving this? Well, again, I have a selection to make my life easier. So I select the vertical walls. I scroll down. I could specify a general inward heat flux, but I'm going to use the convective heat flux. So that exact equation that we saw in the slide previously. Rather than a user-defined coefficient, I'm going to use the external natural convection option. And here we get a sketch of the scenario that we find ourselves under. Let me just close that to make things a bit easier to see. And then we specify what is the wall height. Well, thankfully, I have a parameter that already specifies what this is. And then I need to update my ambient temperature. Next, I need to add in one for the top surface. So that's going to use a different library coefficient. This time it's just a single domain. I select 8. I click on updating, and again using the external natural convection. This time, instead of a vertical wall, I'm going to use a horizontal plate upside. And to differentiate between the two, again, we can refer to the sketch. So we see where the convection is occurring relative to the plate. Again, using a parameter that's already defined, I specify the radius and update the ambient temperature condition. So that's everything that's set up in the physics. I've added in the isothermal domains and the heat fluxes, so those simplifying examples. My mesh is physics controlled, set to extra fine. We built that nice and easy. And then we update our time dependent study. So what we're actually going to look at is not over seconds, but look at what happens over the course of 10 hours. So I'm just going to keep the same output times and have a look at how the thermos flask cools over 10 hours. So one thing to note though, we have quite a large initial temperature gradient between our coffee in the fluid domain and the ambient temperature for the rest of the flask. So in order to help with that, we can show the default solver and just make sure that we capture that initial sharp gradient by specifying what our initial time step is. So we just specify that the first time step that the solver takes will be 10 seconds. Otherwise, it's going to continue using the adaptive time meshing. Something that always helps to keep an eye on the solution as you go is to plot the results while you're solving. So here I'm going to output the default plot every time the solver takes a time step. And we hit compute. So this shouldn't take too long. It has to build the mesh and define the equations, but already we can see our model updating, and it's going very quickly. We get a convergence plot saying how quickly our time steps are, and because we've got a nice simplified convective heat flux boundary condition, we get to pretty large time steps as we see the coffee cooling. We're working in the 2D axisymmetric formulation. We've already got access to our 3D solution. And let's have a look at what's of interest. How quickly is our coffee cooling over time? So we can add in the results, and let's have a look at what that temperature value is. We specify a global plot, and we use the replace expression to access the built-in variables. So here I can have a look under the heat transfer in solids. If I expand the temperature, I get to see this isothermal domain temperature. I double click and it's automatically added. We can update the units so that we're in degrees Celsius, and let's update the name to say coffee temperature HTC, because we're going to come back to this model and update it so that we use the fully resolved model. So let's have a look and just update the plot here a little, just adding in some line markers in all the time points that have been computed. So how long did that take? We can have a look in the messages window. That took 24 seconds. So very, very quick simulation. Right, so having already seen the live demonstration for our simplified examples, let's move on to solving for bulk convection. This is the fully resolved approach. So what we have here is heat being convected by the movement in the velocity field u. We've already looked at examples where we can impose what that velocity is, but in general that's only available for analytical solutions. And so kind of really simplified geometries, and we don't know it. Therefore, we generally have to, for more complex engineering examples, we have to couple this to computational fluid dynamics to compute what the fluid flow is. This is generally more expensive. We have to combine two sets of physical equations, which are computationally quite expensive. And we also might have the case where the temperature gradient is so large that we have a change in density and a change in viscosity. And in fact, we will see this further as we look at the different types of convection that we have. But first thing to highlight is the difference between a heat transfer coefficient and a fully resolved model. I've seen a number of times in support where people want to solve for fluid flow and they wish to say, my heat transfer coefficient is 5 or is 25. But when you're solving for conjugate heat transfer, where you have the fluid and fully resolved and you are accounting for the continuous temperature field between the fluid and solid interface, that's not possible. That's something that's computed by the model and something that you get out of the solution. So how well the mixing occurs will depend on the difference between the momentum boundary layer and the thermal boundary layer. So here we have our thermal diffusivity and our momentum diffusivity represented by viscosity, and that can be characterized by our Prandtl number. So when we're simulating this within COMSOL, we can use a predefined multiphysics selection. The conjugate heat transfer selection automatically gives us heat transfer in solids and fluids, solving for a uniform temperature profile. It gives us domain features that solve conduction only in the solids, but conduction and convection in the fluids. The fluid flow domain is also added, so we can set up our inlets and outlets, and what we need to remember is to set that for only the fluid domains. And we can set this up for laminar or turbulent flow, as we see here. The coupling, the temperature dependency of the material properties, and the updating of the velocity field is automatically handled by the non-isothermal flow node. So here's a slide from a training course that we run, where we like to give our users some great tips on how to use this interface. So the best practice is that every flow should have that has an inlet should have the temperature set by an inflow condition, so that the energy state of the fluid entering the computational domain at the inlet has the correct energy value, and so temperature is constrained. Similarly, everywhere that we have an outlet, we should have an outflow so that the energy that's leaving the domain can do so safely. One thing that you can use to make sure that this is set up consistently within your model is to use selections, as you've already seen in the live demonstration. That way you can use an in condition for inflow and inlet, and an out selection for our outflow and outlet. Then you only need to change that domain selection once and both physics conditions update. Another tip is what happens when you don't know whether the fluid's going to be entering the domain or exiting the domain. Well, in the cases when you don't know that, we have the dedicated open boundary condition, which behaves as both, and we'll see that in the live demonstration. Forced convection is whenever we have fluid flow that is driven, and what it does is increases the heat transfer due to that convective term. How difficult that is to solve and how well the mixing occurs will depend upon the Reynolds number. That helps us characterize what flow regime we are in, where we have low Reynolds being laminar and high Reynolds being higher Reynolds numbers leading to turbulent regimes. So what's the difference? Well, what we have here is a comparison on the right-hand side, looking at the temperature gradient from a hot solid into a cooler fluid. What happens is we have our fixed temperature or relatively steady temperature of our solid, and because we have laminar flow, the heat transfer is purely by conduction across the streamlines. So it's a lot slower. But whenever we have turbulent flow, we have extra eddies, extra mixing, and therefore the temperature gradient is a lot sharper, and therefore the heat transfer is generally more effective. This extra mixing is accounted for by the turbulent kinetic energy that's computed within COMSOL. We have a wide range of turbulent flow formulations available, including RANS models, Reynolds Average Navier-Stokes, where we split up the oscillations, the eddies, the random effects, and we account for these by simplifying the process and adding in extra diffusivity. When also we're solving for turbulent flow, we can use simplified turbulence expressions down at the wall, and by using the conjugate heat transfer, using the functionality in the heat transfer module, then the wall functions for thermal are also accounted for, as well as the momentum. If you'd like to find out more about turbulent flow, again, have a look on our website. We've got a great blog on which turbulent flow interface to use, and that summarizes the different computational cost. These are all available in the CFD module, but a subset of these is found in the heat transfer. Please get in touch if you'd like to find out more. So instead of the Reynolds number when it comes to natural convection, it's buoyancy effects that cause the fluid to move, and the high temperature gradients, velocity gradients. So what we use to characterize whether the flow is laminar or turbulent is actually the Rayleigh number. So looking at the effects of buoyancy versus the viscosity here. And so the thermal boundary layer thickness is slightly different. This is much more computationally expensive than using a heat transfer coefficient. It's also important to remember that it's often time dependent. So when you're trying to solve for a stationary problem, again, have a look at our blogs for more details on these different techniques. But our demo today, we're going to be using a transient problem. Okay, so a couple of extra details just to highlight how to use natural convection. Well, the buoyancy effects are proportional to gravity. So gravity can be enabled within the fluid flow interface by simply clicking a checkbox, and then the hydrostatic pressure is automatically compensated for. Additionally, the compressibility to account for that variation in density due to temperature can be set up as weakly compressible, and the non-isothermal flow coupling synchronizes the density across both the heat transfer and the single phase flow interface. If you want to know more about the different natural convection models that you can use, again, have a look at our website. Here's some screenshots of some blogs that are relevant to this area. But for now, we're going to jump into the live demonstration where we have the extended coffee cooling. So we're going to retain the isothermal domain, but we're going to replace the heat transfer coefficients with the fully resolved model. So first things first, we need to update our geometry, so we can add in a block, a rectangle that's going to represent our air domain. So let's put in 0.1 of a width and 0.5 in height. There we have the air domain around the flask, and then we're going to add in our physics. So I can click on the physics tab here, add in physics. I get a window on the right hand side, and I'm going to add in the laminar flow interface. Add that to my selection, and while we have this interface active, I'm going to enable the gravity, and I'm going to select this on just the air domain. This is the new domain that we've added. I'm also going to use this Add Multiphysics wizard to automatically couple the laminar flow, and this will automatically update the compressibility. So watch this. I add this to the component. it knows straight away by default that the coupling is only relevant wherever I have a fluid domain and a laminar flow domain. So nothing is active at the moment. But let's have a look. See, it's automatically switched to incompressible. Okay, so we need to edit the solid domain first because we're still going to use air in here. So this is just a wee trick so that we can specify what the pressure is to use for the material properties. I right click and add in a fluid domain, and this time I select it. Notice this is the same interface. It's one interface for continuous temperature. That's me added the fluid domain, and automatically the heat flux, the convective heat fluxes, they're overwritten. So I don't need to worry about that. It's automatically coupled now, fully resolved. So I need to specify my boundary conditions for the exterior domains. I select the open boundary condition using our ambient temperature. I'm just going to use the graphics window, and let's close that window there, making it easier on the eye. There we go. So I now need to set up the laminar flow settings. Pretty much everything is there. The gravity node is already set up in the Z direction. My initial values are already compensating for hydrostatic pressure. And we can see how that is handled with the equation seen in COMSOL. Next, we need to update and add in an open boundary condition for the fluid as well. So we do that, selecting the same two boundaries. And now when we look at the non-isothermal flow node, we have the selection, the only one where we have the fluid and laminar flow being solved for. Okay, so I'm now going to add in a second study to solve this fully resolved model. So let's go into the study tab, add in a study, and select time dependent. I add that study, and we would then want to update our the times. So again, we're going to look at the solution over 10 hours. But to fully capture the startup effects, I'm going to have to specify some extra times and allow me to set this up. So let's start from these time settings, look at 10 hours. And I need to activate the default solver settings again, because I'm going to make sure that I force the solver to take a time step between each of those time points. So I can do that accessing the solver settings and just making a small tweak here to use strict time stepping. Now this is going to take a lot longer to solve, but I want to make sure that things are happening as they should be while I run the simulation. So here's a great trick, a great technique. If you right click a study and say get initial values, it will set up all the data sets and default plot groups before you even start running your simulation. So here we see a velocity plot. So I'm going to make a couple of changes. Firstly, I'm going to change the color table to something that looks a bit more fluid-like. And then I'm going to right-click and add a deformation. What this enables me to do is to be able to visualize the fluid flow solution as well as the temperature solution simultaneously. So I plot that, and we see that's the temperature profile on the right-hand side. I right-click, add in a second surface solving for temperature. Here we want to look at it in degrees Celsius, and I'm going to use a different color table. This time I'm going to use the heat camera. So there we see we have our solution. This is what it's like at time equals 0. And using the results while solving, we can plot this edited plot group as we solve. So we move that to say time steps taken by the solver and hit compute. Oh, one thing I forgot to do, because this is going to be more computationally expensive, it's quite important not to use too fine a mesh. So I'm going to drop down from extra fine to finer using the physics controlled mesh, and look what happens now that we've added in fluid flow. We automatically have extra resolution normal to our solid fluid interface. So we hit compute, and then we will start to see the plot once it starts up. So there we go. We can start to see the temperature gradients forming. The velocity is beginning to increase from that zero solution. And as we let this solution progress, we'll start to see the heat will cause the fluid to rise. And as it shoots up the way, we will then start to see some kind of recirculation zone in this region. Okay, this is going to take some time to solve, so I'm going to switch to a model that we already have solved. And this is us plotting after 10 hours, and we can see that circulation zone as we expected. So what the heat let's have a look at the comparison between the two formulations. I've just added in the same plot group, but this time added in the fully resolved solution here. And you can see that after 10 hours, there's maybe a degree or two of difference. So in terms of the computational speed, 27 seconds versus how long did this one take? 5 minutes. That's quite a big change. So one thing that's not captured, as I said, are these recirculation zones. So that is a limitation, but it all depends on how much accuracy we're looking for from our model. Okay, that concludes the live demonstration. So let me jump back. I just want to say, what is my heat source? Well, it can be anything. COMSOL Multiphysics can be coupled with all the other interfaces to solve for any kind of heat source. So here's some on the screen. We have dual heating, inductive heating, and this can also be coupled with things like thermal expansion and phase change. So talking of phase change, that could be a fluid. There are many different ways to model heat transfer in fluids in COMSOL, and I've added some extra ones that we've not had time to cover today. Rotating machinery, porous flow, moisture transport, high Mach number flow. You can couple with particle tracing and simplified examples like pipe flow. It's a really, really interesting topic, this, and we've only just been able to scratch the surface. So with that, I'd like to move on and have a look at some of the questions that have been fielded today.
Thanks you for your presentation, Andrew. So we're open for questions now, and I can see we already have a lot of questions, so thank you, audience. So the first question for you, Andrew, can I add radiation to my simulation?
Yes, you can. There are a number of different ways you can account for radiation in COMSOL, but the most common would be surface-to-surface radiation. And of course, it's worth noting that by default, through a fluid, it will be considered transparent. So you can do surface-to-surface radiation between gray bodies, so that would be from a solid to a solid, but that can be coupled in with your convective or fully resolved model as well. So great question.
Thank you. And straight to the next question. Which method discussed today do you recommend?
That's a tough question. It entirely depends on the computational resources you have and the degree of accuracy that you want. But in general, I would say start with the simplest, making sure that that behaves as you expect, and add complexity one step at a time. That's always the way I try and do it. I sometimes forget, I take a step too far, and it takes me a lot longer to work out what's gone wrong. So I would start with the simplest and build up gradually.
Thanks for your advice. So can I include thermal expansion?
For solid, that's pretty straightforward. You can couple that with thermal expansion, solving for using the solid mechanics interface, and using fluid structure interaction. You can also allow that change in shape of the solid to affect the fluid flow as well. So that's how I would do that one.
Great. Next question for you. Is it possible to solve for heat transfer in multi-phase flow? Thanks.
I think I can jump back a slide here, actually. You can extend it with two-phase flow, but the challenge here is that the thermal properties need to be set up so that they vary between the phases. So you can use, whether you're using the level set or the phase field method, which is one of our separated, separated multi-phase flow formulations, you can change the thermal conductivity between the two phases. If you have the microfluidics module, though, you can use the two-phase flow moving mesh, and that becomes a lot more straightforward because then the fluid domains, the fluid-fluid interface moves, and therefore the material properties move with it, whereas the level set and phase field methods have a fixed mesh but a moving interface, which is solved with a color function. So again, have a look online. We have a wide range of resources on our multi-phase flow capabilities, but no, that's an interesting one, and I have seen it done.
Great. Next question for you. How can I incorporate measurement data in COMSOL model? For example, heat flux versus temperature.
Well, the best way, I'm going to have to jump to COMSOL for this, and the best way to incorporate any experimental data is to use a built-in function. So if you have that data, you can specify an interpolation function where you can either specify a local table, even a results table from another model, or you can import that from a file, whether it's from Excel or any kind of tab delimited data, and you can import that. That then defines a function, in this case int1, and you can specify what the arguments are for the input variable and the output for the function. So I think you said something like a heat flux, so watts per meter squared would be the input argument, and the output would be a temperature in Kelvin. So that's how I would go about doing it. And then anywhere in the model, let me just pick something and change it. You can then refer to that function using syntax, int1, the name of the function, and then input your heat flux, like so.
Great, thank you. Next question for you. Which modules are suitable for drying process?
Oh, again, it depends on what type of drying process you're looking at. But the best off-the-shelf functionality is found, again, if you can see the slide on additional heat transfer and fluids, it's the moist air and moisture transport. So we have dedicated moist surfaces and wet surfaces that can't handle the actual condensation, but it is really good at solving for drying process. And so you can account for the evaporation, including the latent heat effects, as you have that phase change from the liquid phase into the gas phase, which can then be transported in the moist air functionality. So again, I hate to sound like a broken record, but we have blogs on that on our website. So please use those resources and have a read at the different moisture transport capabilities.
I think we have just one more question. Time for one more question. Is it possible to use automatic mesh refinement?
Oh, yes. Oh, yes. That's standard functionality for all COMSOL models. That's found in some of the solver settings. I don't have time to kind of open that up, but yeah, if you want to find out more, get in touch with support@comsol.com and we can guide you to a relevant example.
Great, thanks, Andrew. So that now brings us to the end of the Q&A. Any unanswered questions will be followed up after today, and sorry we didn't get the chance to reach them immediately. A lot of questions today, thank you so much. So we do have a lot of additional resources which might help you to learn about today's topic and other COMSOL capabilities or applications which it can be used for. So if you would like to learn more about COMSOL multiphysics and in application building in particular, you can access additional resources on our website, ukcomsol.com. On the homepage, you will find the link to download the Introduction to COMSOL Multiphysics and Introduction to Application Builder booklets in PDF form, which contain all that you need to get started, including step-by-step tutorials and insights to setting up your model or application. Also on the website, as Andrew mentioned, you can find a regularly updated blog with a range of informative and useful physical and simulation-based topics. Also, there are a number of user stories demonstrating how other COMSOL users use the software and COMSOL server to meet their simulation needs. And we have just launched the COMSOL Learning Center, which we're really excited about, where you can find many videos to help you learning how to use the COMSOL Multiphysics software. COMSOL will be hosting our annual European conference in Cambridge, UK next year on 24th to 26th of September. Please save the date. The registration will be open soon, so please keep an eye. It's a great opportunity to meet other COMSOL users, listen to keynote presentations from very, very well-known organizations, also promoting your work by submitting your papers and posters and presenting in front of other users. Also attending various panel discussions and listening to industry experts, and so you have a chance to ask them questions. If you would like to get in touch with COMSOL to ask us any further questions about what you've heard today or anything else, you can do so at the link given on the slide. Additionally, there is a direct link on the website banner to request a live demo of the software if you haven't used it before. So this brings us to the end of the webinar. Please fill in the very short survey to give us your feedback that will appear immediately after the webinar is finished. We value your feedback. Please advise us on other topics you would be interested to hear from us. Thanks again for attending our webinar. Have a great afternoon. Thank you.